So when I first submitted the talk, I called it Issues in EVM Equivalence, but then I realized issues are forever, adventures have conclusions. So all these things I'm going to talk about, there are solutions to all of these various problems in EVM Equivalence. So quick agenda. This looked a lot better on Google Slides. I'm going to talk about what is EVM Equivalence. Then I'm going to talk about RPCs, consensus data, pre-compiles, and then accounts. And I could spend an hour talking about all the various issues, but these are just the top 4 issues that I'm going to talk about. So the first question, though, is what even is EVM Equivalence? I mean, it's a big old buzzword that's going around, and everybody wants it, and it's very important. But you try and get a standard onto what people mean when they say EVM Equivalence, it's a lot harder to figure out. And so I'm going to look at it from 2 perspectives. One is the top-down perspective, and one is the bottom-up perspective. And the top-down perspective, I think, splits into a number of different facets that you might look into the EVM. If you're just using MetaMask, all you care about is that your wallet transaction goes through and it works. If you're writing a smart contract language, all that you care is that it executes the same way on every chain. And if you're running like a MEV operation or a DEX operation, you need to be able to access the EVM reliably and have it do the same things in the contracts you deploy in all cases. And finally, there's the actual execution. When you write a series of bytecodes, you want those bytecodes to mean the same thing in the same places. And those are 4 different perspectives onto what EVM Equivalence means that really have 4 conflicting different views as to what you get out of it. Now, most of us here in this seminar are probably talking about the lower right quadrant, smart contract execution, but all 4 of these are relevant. The second approach I want to talk about is coming from the bottom up, and that is where do these EVMs come from? And I've broken it into 3 different categories of EVMs. The first one is what I call consensus derivatives. These are chains that are driven off of a variation of a core client. For example, they'll take geth and they'll change the way the consensus works. And that's just a derivative of the EVM. The stuff that they're not concerned about, the consensus things, are going to be the same, so you're going to get a lot easier experiences there. The second form is the ZK EVM, and this is where they take the definition of the EVM and they re-implement it in context of what they're going to get, of what they want to execute within the EVM and within their ZK proving systems. So they need to re-execute everything from the beginning, but they also got a lot of different problems relating to things that are easy in ZK that are hard in regular programming, that are hard in things like C and Java and Go, versus things that are easy in C and Java and Go that are really hard in ZK EVM, like doing Kachak as a cryptography. And then there's an important third category, and this, I think, is the more interesting one for EVM Equivalence, and these are the independent implementations. These are blockchains that didn't start out as EVM equivalent, but later on, or maybe from the beginning, they added it on, and they brought it in not because they wanted to have smart contract compatibility with the ecosystem. So they've got to map things onto their system that didn't derive directly from an EVM system and make it behave the same. And that's where some of the more interesting challenges lie. So to start off with, how would you do EVM equivalence? Surprisingly, we need to talk about RPC. RPC is the gateway by which you approach the Ethereum virtual machine. If you want to use any sort of an EVM program or transaction, you want to use all the available tooling, they all go through JSON RPC. So if you're going to be building a system that is EVM equivalent, you have to support the standard RPCs. Even though that has nothing to do with bytecodes, it's how all the tools interact with it. And the tools that do debugging, the tools that help you write the code, the tools that help you deploy it, all go through JSON RPC. Now the funny thing about JSON RPC is if you have an independent implementation that has a native token system, you can make it act like it has ERC20 tokens without executing a single line of EVM code. You can create that front. To some people, that's all they care about EVM equivalence. When you start doing things like deploying contracts and doing create2 DEX implementations with Uniswap, suddenly things get really, really complex really quick. So it's an iceberg. The surface may be really simple, but the more and more that you develop, the harder and harder it gets. And one of the problems as a former front-end developer, all bugs are UX bugs until proven otherwise. That's one of the bad news for the people doing the RPCs, is when they get something that doesn't work, very quickly they need to say, it's like, oh, no. This is something that the EVM is executing wrong. It's no longer an RPC code. So when you get these errors, and they'll have bad messages, they look like RPC errors when they're actually deep EVM equivalence problems. The next area of concern is consensus data. And I'm talking about the opcodes where you get data from the block structure and you bring it into your EVM experience. But first I want to talk about, to frame it, something that I learned at Google. And this is one of those software development laws that you hate because it's 100% true. And that is Hiram's Law. And what Hiram's Law states is that when you implement something, the side effects are forever. And I'll just read it because I can't phrase it any better than Hiram wrote it. It says, with a sufficient number of users of an API, and he's talking about software, it does not matter what you promise in the contract, and this isn't like a smart contract, this is like your documentation. All observable behaviors of your system will be dependent upon by somebody. So even though you didn't intend for the difficulty opcode to become an excellent source of pseudo-random numbers if you're only relying on the low bytes, even if you say, don't use this because someday difficulty is going away, it's going to be set to 0, somebody's going to use it, and they're going to depend upon it for pseudo-random numbers. So here's a set of strategies of how people were handling equivalence for some of these block values. The values on the left here are just listing some of the easier ways of how you could map some of the systems. There are systems that have blocks they don't have blocks that have sequences of transactions. So there's ways you can emulate it by using your transaction position to create a hash, and also the timestamp and the number, but some of the more interesting ones are on the right. One example is what Ethereum did with the difficulty opcode. They replaced it with another piece of data from the consensus headers called pre-Randau, which solved a lot of lottery contract problems because pre-Randau is actually a better source of pseudo-random numbers than difficulty was. But if you really want random numbers, don't use anything that's coming from the EVM, use an external service like an Oracle. That's where you can get your real reliable randomness, because anything that's in the EVM can be gamed a lot easier than anything else. But then there's a couple of other things that you need to worry about. Does your system implement something like EIP 1559 for transaction pricing? Because with future versions of the EVM, you have to support an opcode. If you don't, there are sensible values you can return from base fee. Just say 0. Another thing that's going to be happening sometime next year is the Cancun upgrade. Does your blockchain system support blobs? Maybe it does, maybe it doesn't. But there's new opcodes that you need to support to provide reasonable values. It's really easy with these two. Just say 0 for blob hashes. There's no blob hashes attached. And 0 for blob base fee because you're not supporting blobs. But that brings us into another subject. They added another precompile in Cancun that I think is the best way for precompiles going forward to be dealt with. The 4788 precompile is they just put it out they defined it in EVM and they brought it in, and every client's implementing it by hand, but you could do it through EVM. So I want to talk about the next issue, which is precompiles. But first I want to talk about some language changes that I think we probably should adopt in the industry. I think there's two kinds of precompiles that people generally talk about, and they deserve two different names. The first kind of a precompile is genuinely precompiled EVM code modulo gas prices. If you can express your cryptography in EVM, but you can do it faster and more efficiently in native code, that's a precompile. And that's when they started writing the precompiles, that's what they intended. But if you're accessing something else within your system, like layer 2 messaging data, like if you have a native token implementation in your system, or if you need to access special privileges for transferring money in the system that may not be exposed in the EVM, they look like precompiled contracts, they look like contracts, but I think the phrase we should actually start using is system contracts, because these are contracts that interact with the system in ways that the EVM does not allow you to do. And I think this is the best way for us to get at the system rather than adding opcodes. In fact, for more of these block header values that are going to start coming into the EVM, I really think in mainnet, the next time we do this, it should come through a precompiled contract, because that'll make it a lot easier for EVM implementers going forward to implement this through a system contract. And if they don't support that particular block value, they just don't expose that system contract. So the standard precompiled contracts are kind of an interesting story. If you are if you're a consensus derivative or an independent implementation, implementing these is relatively easy because you just linked in a native library. The ZK EVMs, however, have an incredibly difficult time with a lot of these precompiles. Maybe mod.exp will be implemented, but all the others will throw errors and won't allow you to execute them. So ZK EVMs have the hardest time with these precompiles because they just are completely opposite for what ZKs need to do, and they're also a lot more expensive to do in ZKs. It creates, just like some of these hashing algorithms are just incredibly difficult for them. And so they take a variety of approaches in solving these. Some of them don't support them. And another group, they'll support them, but they won't put the data into the ZK validity proofs. We'll see how that approach works out. System contracts, however, I think are the future of integrating with consensus in the EVM. One example that we have that's going to show up today is the 4788 beacon root contract of how we're exposing all the data through a stateful precompile, a system contract that has special privileges that accesses data outside the system. Some other common things you might do with it is accessing a native token system, layer 2 messaging, perhaps you have some weird things going on with your fee schedules. A PNRG, you might have an even better solution to PNRGs than pre-VRAN DAO. But these are going to be the best way to provide custom access to your system without breaking EVM equivalence. In my opinion, if you add a system contract, that is not breaking EVM equivalence. And if you don't have a system contract that mainnet specifies, I also wouldn't say that you break EVM equivalence as opposed to, say, not implementing an opcode. Because, return data size is the old push 0. So again, Hiram's law strikes there. If you expose something as an opcode, people are going to use it in ways you don't want to use it, and you can't just get rid of it. But a precompiled contract, it's like the account's not there, and everyone should be able to handle situations like that. And the last thing I want to talk about for EVM equivalence is accounts. And this is where things get really deep really, really quick. The account semantics are subtle. If you're a consensus derivative, this is going to be free for you and easy. If you're a ZK system, it's probably going to be easy because you're not mapping onto an existing system. But if you have account abstraction, if you add new features, it's going to get harder. But if you're doing an independent implementation that has its own blockchain structure with its own account rules, and you're trying to layer the EVM into it, it's going to get really difficult. This is an awesome AI-generated image. I said, give me square pegs and round holes. And I think this is just the best expression of what it's like as an independent implementation, trying to get the EVM to treat your account just like an EVM account. There's just so many ways that it just doesn't quite fit. So here's just kind of a laundry list of some of the issues that I had. Account addresses are the first one. Some systems don't use hash-assigned addresses. Near gives you names. Hedera starts counting from 1,000. So if you want to port something in like Uniswap in, you're in trouble because Uniswap absolutely depends upon create2 generated addresses. So you need to create a system in there that'll map your alias, these short account numbers, into the hash derivative numbers. Apologies for the formatting. I don't know what happened when these slides went through the system. The next issue is nonce management. Like it or not, you have to have nonces. Little things like the number of decimals. I know MetaMask says there's an API that says your blockchain can support any number of decimals, but it ignores it, and everything's 18 decimals. So if you want quality EVM equivalence, you need to support 18 decimals for your native token. And then the final one, ones we had all sorts of fun with in Hedera, is non-existent accounts. In Ethereum, it's fine calling non-existent accounts and creating non-existent accounts out of thin air. That's easy. In Hedera and Near and other systems, this is really hard to deal with. And it makes things like counterfactual contracts really difficult. So you need to have some sort of a solution to address that. And finally, this was mentioned in another talk, delegate calls to system contracts. It's a great way to bring concurrent vulnerabilities, common vulnerability exceptions notices into your system. There have been many exploits that have done with these if you allowed your system contracts to be delegate called. So the simple answer there is refuse to execute if you notice your delegate call in a system contract. So those are the issues that I have found in trying to bring EVM equivalence to the systems. And as you see, it's just a lot of little fine details. If you have any questions, you can get a hold of me on Twitter at Shemnon or on warpcast@shemnon.eth. Thanks.